Okay, so here we go. So last time we were talking about surface integrals. So just a very quick review of surface integrals. So the big idea is that if you have some quantity that's accumulating over a dimensionally awkward domain, in this case we're entertaining a surface that's an intrinsically two-dimensional thing that is actually living in a three-dimensional world, right? So if something is accumulating over such a domain, how would we compute that? And the idea we came up with was to, again, just kind of chop it up, add it up, Riemann sum, right? Okay, so thus the idea of a scalar surface integral. And from the previous section, we had already actually laid a bunch of groundwork that allows us to pretty much just kind of write down the details of how to pull back through a parameterization. And then we saw, various examples. Next, we tried to apply these ideas to a different physical scenario of flux, right? And what we find is that flux is a different kind of a physical scenario. For one thing, there's this matter of orientation. It really matters which direction you're talking about moving through the surface. There's a minus sign involved if you decide one way versus the other way, right? And there's absolutely no such thing when you're talking about mass, for example, right? Mass is you just literally add up the pieces of mass, add up in whatever direction you like, who cares, right? Okay, so taking some of the ideas of a scalar surface integral, but adapting accordingly, given this idea of an orientation, we get a related but different expression called a vector surface integral, which for the moment, our only interest in vector surface integrals is for this idea of flux, right? Which specifically we're only interested in so far for the physical scenario of a fluid passing through a surface and wanted to keep track of the flow rate, right? And side note, that's going to broaden pretty soon here. Okay, so anyway, vector surface integrals, which I sometimes call flux integrals, how to compute them. Again, we use the same kind of, groundwork previously laid and have just a matter of, again, sort of plugging in and pulling back. Okay, all right. Okay, so and we saw an example. Now, we then had to recognize that there is an awkwardness about pulling back through a parameterization. We basically didn't notice the analogous problem when we were talking about vector line integrals, because in the analogous scenario, we have a good geometric intuition for what it means to parameterize something in a certain direction. If you're going to parameterize a curve, well, just make sure you start with t equals 0 where you're physically starting, and then make sure that as t progresses, it moves you in the direction you're supposed to be going. And if you want to rewrite that in terms of a velocity vector or something like that, easily done. Fine, no problem. The analogous scenario is just really hard to see coming. We just don't have this intuition for which direction have we parameterized. So when a surface comes to you, let's see here, yeah. When a surface comes to you with a choice of an orientation, right? This is what we call the orientation unit normal, indicating which direction you move the surface. When you parameterize, you got to recognize that your parameterization will create a different, potentially different, right? I'll say a disconnected, right? Unrelated unit normal from your parameterization. And thus there is this possibility that, depending on which way this surface was supposed to be oriented, the parameterization that I created, that's a coin flip as to whether I would have parameterized it the way I should have or whether I got it exactly wrong. Okay, so this is something you have to watch out for. And this was where I recognized the little slight, subtle error in the calculation on the previous page. And the punchline is you are now sort of obligated to do stuff like this. You have to look, when you're looking at a flux integral, you have to look at the given orientation for your surface. You have to look at the orientation that results from how you arbitrarily chose to parameterize, and then you have to compare. You have to pause the calculation, ask yourself, are these the same? Right? Did I parameterize it the way I was supposed to, or perhaps not? Right? And of course, in this example, we've already gone through, we did not. We parameterized it upward when it should have been downward. Right? And when that happens, you fix it with a minus sign. Now, again, it's very important to put that minus sign in the correct location. Again, if in some scenario where all you care about is the answer at the bottom of the page, then I suppose in that scenario, then it wouldn't matter where the minus sign is. But that's not where we are, right? So the reasoning matters, the argument matters, and so where the minus sign appears matters. And specifically, the point here, this ds comes from the given orientation of the surface, right? That ds, the ds vector comes from the surface. The n vector, as you see here, comes from the parameterization. So it's in converting from ds to n, this is where the minus sign has to be. Okay, so I hope that all makes sense, and I think this is where we left off before Thanksgiving. I hope everybody had a good Thanksgiving break, nice and relaxing. As I was telling my students this morning, mine was arguably too good. I got too accustomed to taking it easy and relaxing, and anyway. All right. Okay, so here we go. New stuff. How should we talk about this situation right here, where, let me clean up the mess to be clear here. How should we discuss this situation where, this is got a positive z-coordinate. This normal vector is positive z-coordinate. I was supposed to parameterize, downward, whatever that means, right? Now, of course, it's not straight downward because the surface isn't pointing straight down. Right? So how do we talk about this? The big point that I want to leave you with on that is to keep in mind that the purpose that language serves in this scenario is not to be precise. The purpose is to be unambiguous. Right? So there is no single word. For example, if I want to talk about this orientation right here, the one that's pointing, you might say upward. Well, there's no single word that's going to describe exactly which direction these vectors are all pointing. Right? So don't try. Right? We don't need a single word that will describe exactly which direction these are pointing. What we need is a word, or typically a pair of words, that distinguishes these two possibilities from each other. And the vectors that I have labeled in green here, these vectors are all pointing at least somewhat upward. The blue vectors are pointing in no sense upward at all. So upward, unambiguous, clearly picking out these green vectors. Does that make sense to everybody? Okay. All right. Likewise with the blue, downward. Again, all of these blue vectors are pointing at least somewhat downward. None of the green vectors are pointing in any sense downward. So downward, unambiguously picks out the blue orientation versus the green. So likewise with these other examples. So I don't make the mistake, please, of thinking that upward versus downward will always be the ideal choice of words. In this case, for this surface, yes, it's a highly unambiguous, very useful choice of words. But if you look at, let me just erase that there. If you look at these two orientations, where I have this green is one of my orientation options, and then what I have here in blue, this is one of my. This is my other orientation option. If I were to try to say upward versus downward to distinguish the green from the blue, well, it's useless. Some of these green vectors point upwards, some don't. Some of the blue vectors point upwards, some don't. Upward doesn't distinguish between these two orientations, right? But conveniently, inward versus outward does a great job, right? Those blue vectors are all pointing inward unambiguously. The green vectors are all pointing outward unambiguously. So that's the better language for this surface. So it would be nice if there were some better solution than this. I'm not aware of it. You have to just be very careful and thoughtful about the nature of the geometry of the surface you're looking at, and tailor your choice of words to, again, not precisely, but to unambiguously distinguish the two orientations. Okay. All right. Everybody okay with that? All right. Okay. Good news. Sometimes you get lucky. Not everything is a massive plug and chug, in other words. So let's consider this case here. We're going to look at our surface here being the sphere rho equals 3 oriented outward. So our orientation vector needs to be that way. And then let's see here. We're interested in the flux, apparently, of this vector field given by that formula. And it just, if you look at the statement of the question and don't look for sort of a freebie, this is kind of a scary question. Pretty scary if you think about how do we parameterize these things. This I would parameterize with the spherical graph parameterization, which is full of trig, which means there's going to be trig in each one of these things here, right? Which means furthermore there's going to be a lot of trig in our capital N vector, and we're just going to have a massive trig explosion, right, that we're going to have to deal with. And those integrals can be unwieldy sometimes. So not really an encouraging approach. So here's what you should be on the lookout for. And by the way, the tip-off here is the fact that this is a sphere centered at the origin. We love spheres centered at the origin. Tons of symmetries, powerful symmetries, very useful. So because of those symmetries, this unit normal vector here, pretty easy to write down a formula for it, because spheres, very conveniently, always point in the same direction as the position vector. And again, this feature is unique to spheres centered at the origin, right? That the outward normal and the position vector always parallel. So that's one of the reasons whenever I see a sphere, one of my first thoughts is, okay, how are we going to get lucky here? Where is the good news? This is one of the possible good news to be on the lookout for. Being as it is a scalar multiple of the position vector, and of course a unit vector, it's pretty easy to see what the formula is for that normal vector. And with that observed, take your formula for your vector field. And notice that you can just crank out this dot product directly. And it turns into 0, and we're done. I didn't have to parameterize anything. There's no trig on the page. We avoided all of that trig ugliness, right? Again, key observation about, because this is a sphere, really easy to write down a handy formula for that unit normal. Is everybody okay? Here's another example. This is a different kind of geometric good fortune. Here we have as our surface, let's see here, we have, oh gosh, it's a certain part of a certain plane. Which part of that plane? Well, it's a awkwardly described portion of this plane on which we want to compute the flux of this pretty scary looking vector field. So this at a glance looks like a brutal problem, right? So discouraging, but good news. And again, always be on the lookout for, how can I capitalize on good fortune that is in my problem somewhere. The good fortune here is in the fact that my surface, weird though it is, lives entirely within that plane. And that's really handy information. Flat is awesome, when you're doing surface integrals. So a couple of ways that this is beneficial. So for one thing, if y is equal to 3, then that means I can pop that into that factor right there, which means I get a 0 in one of the coordinates of the vector field, right? So keep in mind, we're computing this flux on our surface S, all of which is in this plane, and therefore y equals 3 is valid for every point in our entire domain, and that means that, again, however weird this formula here might be, it doesn't matter how weird it is, where we're looking, that second coordinate is always 0. So again, capitalize, right? Take advantage of that. That's super handy. Second big win, and again, because of the fact that we're looking at part of this plane, y equals 3, which direction is perpendicular to that plane? Pretty immediate, right? The plane y equals 3, I mean, again, there's a nice easy picture. It's, vertical, parallel to the xz plane, and so, well, the normal vector's got to be this, keeping in mind the orientation. We're in the positive y direction, not the negative. So that means that this unit normal vector, I can write that down immediately as well. And again, notice now I haven't parameterized, right? Not that I couldn't do it, but I don't have to. And because I didn't have to, you can take advantage of the fact that this product works out to be super convenient. That dot product is 0, therefore this integral is 0. And again, we saved ourselves loads of trouble. Everybody happy? Yeah.
So in the last two examples, the integral has been equal to 0.
Yeah.
Is that just that just happened, or is it always going to be like that?
There's no always. Yeah, sad. It would be nice if there was an always, but no such luck. No, the symmetries that I'm showing you happen to work out in this case to where they turned out to be a 0. But I could imagine some other scenario where maybe different vector field, different surface. Maybe this dot product might end up being 3. And then at least then you change the question to, well, I just need to multiply 3 times the surface area of that vector. Something like that. Yeah. So, yeah, sadly, no such luck on the always 0. Yeah, yes.
Would it be wrong to plug in 3 at the top, like x cubed?
Oh, yeah. No, that's right. It'd be perfectly fine to plug in y equals 3 here. That's right. The only reason I didn't bother with that is I kind of didn't need to. But you're absolutely right. This y right here could totally be a 3. I didn't bother because I knew I was going to have a 0 here, and I knew it was going to go away.
So if it wasn't going to go away, then that would be 3.
Yes, absolutely. Yeah. Anybody else? Okay. All right. Yeah. Okay. So y'all will recall, I'm sure, when we were doing vector line integrals, that we wrote down what turned into a weird notation for how to represent vector line integrals. And the term that I used is coordinate line integrals, right? And so we, instead of writing integral f dot dx, we could instead write integral p dx plus q dy plus r dz, sort of a notational alternative, which, like, why, right? So what is this bias? And in Math219, the punchline was it doesn't really bias much of anything. This is an obligation. It's good for powerful techniques for things that we're not going to be doing in this class, and as such, it's in the literature. It's out there. You're going to experience it. Some people like that notation and use it exclusively, independent of whether it's actually beneficial for what they're doing with it. But anyway, so the point is it's out there. You have to know what to do with it. This is the same deal. This is the surface version of what we previously saw there. So let me walk you through the details. It has to do with what we know about our ds vector. Right, recall the ds vector. One of the formulas we have is this right here. Quick aside, I'll remind you that there is this issue with orientations. Right? And you have to be careful with that. It's your responsibility to make sure you've thought about the orientation that's given, the orientation that you've created, let's see, let me highlight as we go here. The orientation that you're given tells you about the ds vector. The orientation that you made up when you parameterized, and then there's a possibility they may be pointing in opposite directions, and you have to account for that. Right? So, okay, that's the plus minus question mark that pervades this page. That's what that's about. Okay, so that said, notice we can write down what n is. I can expand that in coordinates. I can crank out that cross product in coordinates, and that's, you'll got to write down the details for that. But it turns out that not only can you write down that cross product, but each of the coordinates of the cross product is one of these change of variables looking, little Jacobian 2x2 Jacobian determinant expressions that when we were doing change of variables, we developed this notation. So flashback to chapter 5, change of variables. And I want to recognize there's something weird about that. After all, these expressions are two-dimensional change of variables, which is not what we're doing here. We're looking at a surface in space. There is no two-dimensional change of variables that we've recognized on this, right? So that's seemingly a coincidence. Turns out, by the way, it's not a coincidence. There's a really good reason for it. If you're curious, come talk to me. I'd be happy to show you. But that's a 15-minute conversation we don't really need, and so I'm not gonna do it here. But that said, now that we find ourselves looking at our ds vector, we've rewritten it like that, which of course is the same as this. Reasonable question to ask is, okay, well, what should I call, for example, this third coordinate, for example? Just, it doesn't matter. All applies to all of them. But what should I call this third coordinate? How should I rewrite that third coordinate? And now I cringe as I do this. But it's as if that cancels with that. It doesn't. That's nonsense, right? A little math crime. But it's a very convenient memory tool. Punchline being, with that faux cancellation, you see the motivation to call this dx dy. And likewise for the other two coordinates there. So all together then, what we have here is an alternative coordinate-based notation for our ds vector. And that is, we can write it as that thing right there. And now, just like we did when we were looking at vector line integrals, we can take the ds, rewrite it with our fancy new notation, our coordinate notation. We can take our vector field, whatever that is, and of course I'm going to need names for its coordinates, and PQR is a pretty standard choice for whatever reason. So I write down the PQR, and then notice this dot product. I can just straight up crank out by coordinates that dot product. And here is your alternative notation now for a vector surface integral. Vector surface integral can alternatively be written like this. Everybody kind of follow the little algebra there? It's, certain amount of tedium there. But so we find ourselves in the same position as when we discovered the analogous notation. The analogous notation for vector line integrals, which is looking at our two options here. Why would I ever choose this one? It's quite a bit bulkier. It's a lot less sort of intuitively satisfying. F, yeah, that's my vector field. It represents whatever my physical scenario is. Fluid flow or, forces maybe, something like that. That's a real natural physical thing. We have a standing, I believe, fairly natural interpretation of the ds vector. That makes loads of sense. That's a real thing, right? What the heck is dz dx? Right? It's a lot less intuitively satisfying and bulkier. Okay, so why does this persist, despite, for Math219 purposes, it being not particularly helpful? And again, two answers. This notation, weird though it is extremely powerful. It's just for reasons that we can't talk about in this course, right? In deep water, but you can. This is what differential forms, integrals of differential forms look like. As it turns out, you can prove theorems that eluded the 19th century mathematician powerhouses using differential forms. So it is a big deal, and it really does make loads of sense if you're doing some of those more sophisticated things. That said, because of this power, this notation is very popular. Because of that popularity, you're going to see it outside of Math219. So I need y'all to be ready when you see notation that looks like this. I need you to be ready to know what to do. Right? And what I suggest, what I think is most convenient, is when you see something like this, just think to yourself, okay, all right, well, look, the P, the Q, and the R, that's just fancy talk for what my vector field is. And the all of this business here, dy, dz, dz, dx, dx, dy, all of that's just a fancy way of writing the ds vector. And so all of this stuff is just a clunky way of describing vector surface integral. So certainly whenever I see an integral that looks like this, step one for me, I rewrite it like this and then interpret it as the flux that it is. So that's my suggestion. How are we doing? Everybody happy? Okay. All right, moving along. Symmetry. As y'all know, I'm a big fan. Very powerful tool, very convenient. Saved me loads and loads of work when I was an undergrad. Y'all are about to go through an engineering major, many of you anyway, and so it's going to save you lots of trouble. Good news, we have an odd symmetry theorem for scalar surface integrals. So, scalar surface integrals. Notice the way the theorem is written, lays out on the page almost exactly like the way we laid it out on the page for double integrals, and triple integrals, and stuff like that. Scalar line integrals looks exactly the same. It's got the same two little asterisks down here. Again, you got both conditions have to hold. It's not enough to have a symmetric domain only. Absolutely not good enough. Not even close. And again, it's got to be the same plane of symmetry for both of the conditions. Okay. All right, so I'm going to say exactly what you would think. With, again, the same disappointment, and that is it's only for scalar surface integrals. If you are looking at a vector surface integral, like, for example, this, there is no odd symmetry theorem. So keep in mind, if we say odd symmetry would need to apply to the integrand. That's the vector field. That means you would need for the ds, namely little n ds scalar, to be the same on both of these pieces, right, that are flipped over your plane. Well, if that were going to be the case, I would need for the areas, the ds scalars, to be the same on both sides, and well, they are. So that's okay. That part worked out. You might even take some confidence, some encouragement from that fact. But we would also need for these normal vectors to be the same on both sides of the reflection, and they just aren't. Right? You can see easy example here. This is not a particularly weird scenario that I had to manufacture, just a kind of a routine run-of-the-mill symmetric surface. The normal vector is very clearly not the same. Right? So there is no odd symmetry theorem. Don't try. Is that cool? So, but by the way, again, notice the analogy with vector line integrals. Just like we're seeing here, vector line integrals have no odd symmetry theorem, but scalar line integrals do. Just like we're seeing here for surface integrals. Okay. All right. Is everybody happy? Yeah.
Just real quick, what would be like the main difference in application? I don't think I'm entirely clear why you would use like a scalar surface integral, because I know we talk a lot like the vector oriented.
Yeah, the specifics of the application will guide you, right? So if you're writing down, how to compute mass, right? I don't choose to say that mass is mass per unit volume times volume. It just is. You see what I'm saying? Right? And likewise, if I'm computing a flux, right? If I have a fluid, I'm just trying to get back to if I have a fluid passing through a surface, right? On any little bitty, here we go. On any little bitty piece of surface, I don't choose for it to end up with a dot product in it. It just is, right? On these little pieces, that is our established formula for how. You see what I'm saying?
Yeah.
So you don't choose, it is foisted upon you.
Okay.
And you have to deal with whatever your circumstance has dealt you. Yeah. Is everybody happy with that? All right. Okie dokie. Let's see, where are we now? Yeah. Okay, cool. Moving along. So this next thing, it's not really talked about in the book. I think this is a really cool fact, though, for a combination of reasons, one of which is just cultural, but there is a nice sort of Math219 upshot as well. It turns out that vector line integrals and vector surface integrals have a shocking amount in common, and this is really surprising. Let's just for a moment, for example, think about, vector line integrals. What do I do with vector line integrals? I compute, like, work. Okay? Work was our sort of standard motivating example for vector line integrals. For vector surface integrals, there's no work involved. Work doesn't have anything to do with it. Vector surface integrals are about flux. It's a completely different physical thing. So it is unexpected that having been brought to these two different mathematical constructions by totally different physical scenarios, very unexpected that they would actually behave so much alike. And what I want to emphasize now is all the different examples of how they behave almost exactly alike. So here we go. I'm going to draw a line right here to distinguish. We have vector line integrals on the left, vector surface integrals on the right. This is just, by the way, there's nothing new on the screen. Right here, this is all old news. It's all formulas that we've already developed. And let me just kind of go through and kind of compare as we go. So in both cases, we have a parameterization that we use for pulling back purposes. Now, this is a weird way to represent a parameterization of a curve. Why do I have the pullback space up and to the left and the image down and to the right? Well, it's for the annoying logistical matter of the page just isn't wide enough. That's all it is. Sorry about that. That's just the only way I can get it on the page. So anyway, I know it looks weird. Don't worry about that part. Okay, so for each of these, I have a parameterization. For each of these, I look at I'm going to say the derivative of a parametric curve is velocity. And I'm going to call in here the derivative or a derivative of a parameterized surface. And that sounds weird, perhaps, but keep in mind what the formula for capital N is. It comes from crossing the partial derivatives of your parameterization. So it is, after fashion, kind of a derivative. Okay. All right. Let's see here. By the way, notice where velocity shows up in these equations, these old equations that we've had lying around for a long time. And notice as these equations lay out on the page, V and capital N kind of in the same places. All right. Now we also have the unit vector pointing in said direction. In each case, notice where those appear in the equations. And again, notice they are in analogous places in those equations. Let's see here. We have our ds scalar. Let's see. In both cases, I'll use orange for this. Our ds scalar here tells me how long that little piece of curve is. Our ds scalar here tells us the area of the little piece of area there. In both cases, the ds is representing size. And again, notice they appear in the exact same places in these equations, et cetera, et cetera. Right? So just for fun, let me fill in the rest of them. We have our dx vector. Now remember, what we like about our dx vector down here is our dx vector tells us everything that we need to know about this little piece of curve. The dx vector, by its direction, tells you how that curve is oriented, and by its magnitude, it tells you how big it is. In this case, how long. On a surface problem, we have our ds vector. And as we've discussed before, again, this tells you everything you want to know about that little piece of surface. By its direction, it tells you the orientation. By its magnitude, it tells you the size, in this case, the area. So again, the dx and ds vectors play highly analogous roles and conveniently also appear in these equations highly analogously. So it's mysterious how these patterns continue. Notice if you look at the pullback differentials, right? So dt tells you how big your pullback is on the x-axis. Your ds dt tells you how big in the pullback st plane for your surface parameterization. And again, notice they appear in analogous places in the equations. It's kind of ridiculous. Everybody see all that? So now let me tell you why we care about, oh, by the way, the pattern continues. I'm going to let y'all fill in the rest of the color scheme, looking at all these equations all the way down. The color pattern really fits really strongly throughout all of these other equations that, again, we've all already seen. Okay, so 2 reasons you should know this. You should be aware of this analogy. One of them, again, cultural. It's a good thing to know. Even if you don't particularly use the following, I think it's really useful to know that vector line integrals, vector surface integrals, kind of the same thing. All of these similarities that we're seeing here result because we are literally looking at 2 kinds of integrals of differential forms. And again, we can't talk about differential forms, right? It's too much for this class. But if we were to talk about integrals of differential forms, what you'd find is that this is what an integral of a differential form looks like in this geometric context. And this is what it looks like in this context. They're literally the same thing, just in different contexts. So useful cultural note. Everybody okay with that? Any questions? Okay. The other is, I think this is pedagogically useful. So in particular, a lot of students find themselves uncomfortable with the idea of the capital N vector. What do I do with it? How does it relate to other things? It's hard to remember, right? And the strength of the analogy gives you the option of kind of reasoning by analogy, kind of filling in blanks by analogy. So N here we see is the analog of the V vector. And so knowing that it kind of plays analogous roles, it comes from taking derivatives of your parameterization. It relates to your dx vector by way of the parameter differential, and its magnitude tells you the size stretching factor. All of that's true about the capital N vector. So you can take what you're comfortable with, what you understand from the point of view of vector line integrals, and knowing the analogy, that can help you kind of place and make sense out of things you're having trouble with over here. Is everybody all right? Does that make sense? So I hope this will be a useful observation to help you all kind of file ideas in your heads. Okay. All right. Oh, yeah. Okay. Yeah, no worries. Okay. All right. Moving along. 7.3. So 7.3 is another one of these monster sections. You may recall we've had a couple of these in the past, right? So 5.5 5, yeah, was like it should have been 3 separate sections, right? And then what I find entertaining is that the author will then throw in sections like 5.4. That's like one example, right? So there's some size control problems there. Anyway, whatever. So 7.3 is massive. It's going to take us all week plus to get through this section. Just a tremendous amount to say. This is the stuff that Pratt finds most critical, is Stokes' theorem and Gauss's theorem. So anyway, a lot to squeeze into one section. Okay, the book starts with Stokes' theorem. I, like most calculus books, I'm going to start with Gauss's theorem. First thing I'm going to say about Gauss's theorem is that it follows a pattern kind of like Green's theorem. So I think it's a great idea to, as you go through these notes, where I kind of walk you through the motivation for Gauss's theorem, have your notes for Green's theorem open. Right, and then kind of do this move, right, where you're kind of like, okay, so this, all right, well, in this situation we did such and such. Oh yeah, check it out, we're doing the same thing over here, right? So always comparing and contrasting, mostly comparing. So following that pattern, first thing I have to do is tell you what I mean by a boundary, right? Specifically, we're going to suppose that we have some solid three-dimensional region. You'll notice here my three-dimensional region has an air bubble inside of it. Just as a just because that can happen. Right? That said, what's the boundary? Well, the boundary is it's kind of the edge, right? It's the dividing line, I guess it's a dividing surface between where the set is and where the set isn't. Right? So in this case, the boundary has 2 chunks. It has what you might call this inner boundary surface and also this outer boundary surface. Is that cool? Okay, so that boundary surface. Reminder, this notation right here, this symbol looks like a partial symbol. It is a partial symbol. Is shorthand for boundary. Okay, so that noted. You have to keep in mind, from here on out, the word boundary is loaded. It always means oriented according to a certain convention. Right? The word boundary in chapter 6 and 7 always referring to an oriented thing. And we have a convention. Again, these conventions, they're arbitrary, but they are highly standard and we're stuck with them. So again, arbitrary but not optional. And the rule is away from the solid. So now a lot of people will tell you, away from the solid, you look at this vector up here, wouldn't that be reasonable to call outward? A lot of people would say outward. But keep in mind, not all of the boundary is necessarily on the outside. Away from the solid down here, I think you would have to call this inward, not outward. Right? So kind of like the whole, with Green's theorem, always with the region on your left is the rule, right? And it's tempting to say counterclockwise, and that works often, but it's not the rule. The rule is always with the region on your left. Here, always away from the solid. Is that cool? Everybody happy? All right. Again, we're going to be talking about accumulating quantity. I claim boundary flux is an accumulating quantity. Specifically, boundary flux accumulates over the solid. So now, what do we mean by accumulates over the solid? Well, here's a whole solid, highlighted in yellow. And if I were to cut that in half as drawn, I can talk about what you might call the green half and what you might call the blue half. Right, and for each one of these, I can talk about the boundary flux. Of course, boundary, again, loaded word. Right? always oriented what we're going to call away from the solid, but loosely speaking, we say outward asterisk. Make sure to keep in mind that asterisk. So let's walk through now and try to persuade ourselves that this actually is an accumulating quantity in this sense. So, okay, we'll start with the green side. The green side's boundary consists. Whoopsie. I wanted to be in the highlighter mode here. Green side has this chunk oriented that way. And then there's also this kind of the shared face, again, oriented away from the solid. It's kind of that way. All right. Then let's see here. Looking at the R2, the right half, as it were, the boundary consists of that piece oriented away from the solid would be, again, outward, kind of like that. And the boundary of R2 also includes, well, kind of that same shared face, again, outward, away from the solid, away from the thing whose boundary I'm talking about. So away from R2. This is that way. All right. And now the big question, is green plus blue the outward-oriented boundary flux for the whole, right? The whole originally in yellow, right? And the big convenient observation is that if you look at this shared face in the middle there, that shared face is part of the green boundary flux. It's part of the blue boundary flux. It is oriented that way as part of the green. It's oriented this way as part of the blue. This purple face appears twice in our arithmetic, but with opposite signs, it cancels. So this goes away. And notice what remains is, as it should be, the outward-oriented boundary flux of the whole original yellow solid that we started with. Everybody good? Okay. All right, so I do think it's a healthy observation. Look at what we drew here and how the picture looks, and the sort of outward and the whole left-right cancellation, and how that compares. If you go back to section 6.2, which I hope I have pulled up now, I was in the wrong place. Here it is. Yeah. Go back to 6.2. We made, after the fact, an argument about how boundary flux accumulates in this two-dimensional context as well. And there it was a shared edge, not a shared face, right? But again, as part of the boundary of this region, it was oriented that way, and as part of the boundary of this region, it was oriented that way. And so altogether, if I can get my eraser, altogether this edge appears twice, but with opposite orientations and cancels. So it's morally equivalent, right? It's practically the same picture, even, right? Really, really similar to the argument that we just made here. All right, is everybody good? Okay, so we have ourselves an accumulating quantity. When you have an accumulating quantity, the whole is the sum of the parts. And I like to point out that when you have such an accumulating quantity, then you can think of it as having location in the interior. Now, it's a little bit of a trip when you're talking about these kinds of pieces. If you're talking about, all right, well, something about how the boundary flux that happens here is it to some extent happening there, and that just seems completely inconsistent with the fact that this surface here doesn't even touch that surface there. It seems like nonsense. And what that is the right answer to the wrong question. Right? The point isn't where it's calculated. The point is, what does it represent? And when we talk about the boundary flux for the whole, that's representing the interior. It's representing the solid. It's the boundary flux for the solid. We're not talking about surface flux. We're talking about boundary, right? Boundary for the solid that is the actual domain in question. And that region for which we can talk about a boundary flux. And this little sub-region in here in blue, well, the blue truly is part of the green. And if I have an accumulating quantity that accumulates over the green, it stands to reason that a certain amount of it is the amount that's in this blue region, and that you could just compute that by just literally looking within the blue region, right? So it's not that mysterious of a concept if you think about it as how it associates to the underlying solids, instead of falling for the misdirect. Right, the not the point that somehow the surface is what we're interested in. It's the solid inside that we're actually interested in. So again, flux behaves like a stuff. You can think of boundary flux as being like a substance of some sort. And with that said, we're going to have to draw a line. We'll pick up here next time. We're out of time. And see y'all later. Have a good one. Glad to have you back. Hope everybody had a good break.